this talk, I just want to mention one thing. So I realized that when I give this talk, usually people ask questions, and their questions will be answered in the later slides. So I would really appreciate if you could ask questions at the end. I am a really awkward person, full disclosure. So sometimes I joke a lot, but people don't always get my joke or laugh at the point where I want them to laugh at. So I did you all a favor. I have an automatic soundtrack over there that it will laugh. I would really appreciate if you could join it when you hear the sound. OK, so today, well, I promised the conference that I'm going to talk about consensus algorithms. But let's just I lied. We're not going to talk about consensus algorithms. First of all, I have to make this slide work. 1 second. Slideshow. There we go. OK, so let's talk about cakes. So the majority amount of the talk will be focusing on cakes instead of consensus algorithms. Yay, that's a practice run. OK. OK, so first of all, I'd like to start by doing a poll. If you could pull up your phone, and if you could enter this website called Slido. Let's try to display this. If you could just join by entering this code, 3311. Let me know if anyone has problem joining the website. And if you could please look up once you're done so that I know when to move on. So the website is called Slido. The code is 3311. Are we all good? Yeah? OK, let's move on. The first question, have you used any software or libraries that relies on distributed systems? So when we talk about software libraries that relies on it, so it could be simply as email or web browsers. Basically, have you ever been online, right? OK. And if you could please look up once you're done. So I see that we have 2% of the population that has never used the internet. It's pretty amazing. Love to meet you. OK, if you're done, we're going to move on to the next question. Can you describe the details of one consensus algorithm? So by describe the details, I mean, can you explain how it's used, how to implement it, and give some examples of where it's been used? OK, let's see. And please shout out the names of the algorithms if you're really familiar with the algorithm. Just like simply the name is fine. Anyone? Yeah? Oh, wow. Great, Raft. I'm having pressure because I'm going to talk about Raft. What if I get it wrong? OK, don't yell at me if I get it wrong, though. OK, cool. So we have 12%. Wow, that's amazing. And, oh, 13. OK, 50% vaguely. OK, so if we look at the poll result, we can see that a majority amount of people have, well, almost all of us have used distributed system libraries and softwares, but only 13% of us can really describe one of the consensus algorithms, can understand how computers underneath, how they work together. So the purpose of this talk is to bridge the gap between those two and help you to understand how computers have consensus. So let's switch back to the slides. First of all, let's define what is a distributed system. You can think of it as components that locates on different parts of the network, and they communicate with each other by sending each other messages and by communicating that way. So some of the modern examples of distributed system would be the web. So you can think of the web browser as the client, and the servers are the servers. Also, when you put URLs in your browsers, it's going to go look up the DNS server, and it's going to find out the IP address related to the host names, trying to get you to the right place. Also BitTorrent, which we use for only Linux distributions. I'm sure none of you have ever used that for downloading any movies or anything, but BitTorrent also is an example of distributed system. A fun fact, in 1920s, American Airlines Central Office used to have this a card for each flight. So they have a deck of cards where the traveling agents would call in and asking, hey, can I buy a seat on this flight? And they would check if the seat is marked as sold. So if it's still available, it's going to sell the seat to the agent. If it's marked sold, then it's going to find an available seat. So this is a very early example of distributed systems where the traveling agents are the client and the central office is the server. Distributed systems are great. They live in our day-to-day lives. We can't really possibly complete, we can't really live without them, right, online. So but there are also challenges that are linked with distributed systems. So one of the problems is we said all the servers, they're components located on different parts of the network. So they need to communicate with each other by sending messages to each other. The problem is that no server has a global knowledge of everything. So they have knowledge of what's currently on their own state machine and what's in the messages that are sent to them, but no server has the global knowledge of everything. So how do we make sure that the server has up-to-date information? How do we detect inconsistencies in the servers? Also, since we're working with so many different servers, they have their own time, so it's possible that we have clock skew. How do we know when there are messages that are delayed or duplicated? How do we know the order of the messages? Since we're talking about distributed system, it's very common and likely that we have concurrent operations on one single object. And when this case happens, how do we make sure that this object is in consistent state? How do we detect inconsistencies? Leslie Lamport has mentioned that a distributed system is in which the failure of other servers over the network, which you don't even know where that server is, but the server's failure could cause your own machine unusable. So how do we tolerate failures of ourselves and other machines? By tolerate, we mean how do we detect them? How do we recover and handle them? So fortunately, we have consensus algorithms, which will help maintain the integrity of your machines, reliability, fault tolerance, and availability. Today we will be focusing on two protocols, Raft and Paxos. Let's start with Paxos. Paxos, compared to other algorithms, has a really colorful background. It was first implemented and designed by Lynch and Liskov. So when they designed the algorithm, they couldn't find a mathematical proof that would prove that this algorithm actually works. So one day, Leslie Lamport found this paper, and he had a very malicious thought. He said, I'm going to prove this wrong. And by the way, Leslie Lamport, if you're happening to watching this recording right now, please don't be mad at me, because I learned all these from my professors. You should totally blame them. So he had a very malicious thought, right? He wants to prove this wrong, but he accidentally proved it right. So he wrote this paper called The Part-Time Parliament, which describes this Paxos Island, a really cute story of how the islands form consensus and how everything works. And he submitted this paper to conferences and to organizations. He got rejected. And he tried for about 10 years before it eventually got accepted. So the problem was that people had a hard time understanding what he was talking about, because he had really fancy Greek names in the stories, and people just simply didn't understand the algorithm. So one day he was in a conference. People said, we read your paper, we couldn't really understand what Paxos really is. Can you just please explain to us? And he sat down, he explained Paxos to people without mentioning the stories. And people understood. It was actually quite simple. And he was really inspired. He went home, he wrote down this paper called Paxos Made Simple, basically explaining Paxos without the complicated stories. And it started making sense. So later he wrote another paper called Multi-Paxos, which is Paxos and complexity. So we're going to talk about basic Paxos and multi-Paxos today. I'll start with basic Paxos. Actually, strike that. We're going to talk about cakes. How many of you, raise your hand, if you have a problem picking between chocolate cake and cheesecake? I definitely do. Really? We only have one or a few people? This talk won't work if you don't have problem with that. Okay, I will just pretend that you all have problems choosing between chocolate cake and cheesecake. It's the most difficult question in the world. So let's say as a group, after this conference, we're gonna all go out. We're going to buy a cake, buy a huge cake, but it has to be one flavor. It has to be either a chocolate cake or a cheesecake. So how does this usually work? Can I get a person to volunteer? Stuart, yay, I know you. Okay, so let's just say Stuart would raise his hand and says, has anyone picked any flavor yet? And people would just say, no, not really, we haven't decided yet. And Stuart will say, oh, why don't we just go for cheesecake? Cheesecake can't be wrong, right? It's always great. So when people would respond saying that, yeah, sure, let's go for cheesecake. And ta-da, consensus. That is Paxos. Bruh, you're supposed to press the laugh button. There we go. Pay attention. So I need you. Okay, so in Paxos, there's this proposer idea. So you have a proposer that would propose a value, and then you have an acceptor that would accept and reject value from the proposer. How this usually works, let's walk through this step by step. So the proposer, one server, will choose a proposal number. It has to be the largest number you've ever seen. It's going to broadcast this to all the other servers by sending out this prepare message. So this step, you can imagine Stuart saying, hey everyone, have we picked any cake flavor yet, right? So the proposer is broadcasting this prepare message to all the other servers. And the other server will receive this message, and then they will check, is this number the largest number that I've seen so far? If it is, we're going to update this max proposal number. We're also going to send back a promise. So we're going to say, we promise you that we will only accept your value if your value maintains to be the largest proposal number. So this is where we respond to Stuart saying that, nobody has picked anything yet, so go ahead and pick something. And now, so once the proposer received a majority amount of responses from the servers, it's going to know it can go ahead and pick a value. So it's going to send out this accept message that contains the proposal number that used to use, and then also a value that is proposing. So it's going to broadcast this to all the servers. And then now the acceptor, that case was Stuart saying, let's go for cheesecake. So now the acceptors receive this value, and it's going to check, is this n still the largest number that I've seen? Basically, it's checking, is this server the same one, the one that I sent back a promise to? So if it is, we're going to accept this value, and we're going to respond to the proposer. And now the proposer gets lots of responses, going to check, did I have the majority of servers responded to me? If I didn't get any rejection, that means my value is chosen. However, if I got any server that rejected my value, that means in the system there's another server that proposed a larger number. So now I have to start over again from the beginning. Once I have a value chosen, now we have consensus, we can go for cheesecake. That's Paxos. So this proposal number in Paxos is basically, you can form the proposal number using the server ID and the route number. The server ID guarantees the uniqueness of the number, and the route number gets incremented over time and is shared among all the servers. All the servers need to keep track of the highest route number. So when you want to generate a new proposal number, you simply increment the max route number and concat it with the server ID. In multi-Paxos, so we say that multi-Paxos is basically a sequence of instances of basic Paxos, and it works around log entries. So once we have basic Paxos, we want to have the proposer act as a leader. So our client will send the leader information to the server, and it's going to send a command trying to ask the leader to process the request. And the leader will use basic Paxos trying to figure out which instance and which command it is we should English is hard, sorry, execute for the current log. And then we're going to pick the value, have consensus, we're going to apply all the command in the previous logs and the current one, and then we're going to finally return the result to the client. So in multi-Paxos, a leader is the distinguished proposer. It's usually the server with the highest ID. Is responsible for sending heartbeats once a while to the other servers. It's also responsible for accept client requests from the clients. So as a follower, if the server did not receive a heartbeat after a while, it's going to automatically assume that the server, the leader has died. So it's going to step up and try to act as a leader and act as a proposer. If everything works well, the follower will just redirect client request to the leader, act as a acceptor. So it's unlikely that there will be two leaders in Paxos. However, it is possible. So in Paxos, it's designed to be able to handle multiple leaders, but it just won't work as efficient because it needs to constantly fight like who has the larger proposal number, etc., instead of processing client requests. Some of the industry example of Paxos would be Google Chubby, the log service, and also Apache Zookeeper, which uses Paxos-like algorithms to help people to implement distributed system services. Okay, let's move on to Raft. Raft was designed by Diego Ongaro and John Osterhart at Stanford. People recognize this as a simpler version of Paxos in the industry. When people say it's simpler, they don't really mean that the algorithm itself is easier. It just means that the paper contains more details of the algorithm so that it's easier for us, audiences, to understand and to implement the algorithm. In terms of performance and fault tolerance, it's equivalent to Paxos. On top of consistency and correctness, the algorithm was designed around understandability. So why did the professors focus so much on understandability of the server? So if you think about it, in the industry, when we have to implement an algorithm to fit into our own environment, sometimes we have to twist the algorithm a little to be able to fit into our own environment, right? So when we need to implement and twist the algorithm a little bit, we really have to understand the algorithm to make it useful, to be able to implement it correctly. So that's why the algorithm was designed around understandability, because they want people to be able to utilize it in the industry. And first of all, they have to make sure that people understand the algorithm to start with. Different from Paxos, Raft work around logs. So let's talk about cakes again. I'm going to pick someone different now. Let's see. Can I use your name? Sorry, what's your name? Okay. Sorry, the second row. Yeah. Mona. Sorry, say that again. Mona. 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 So as a group, again, we're choosing a cake after this talk, right? So we're going to buy either chocolate cake or cheesecake. And now we know that Mona in this room is the best person to pick the cake flavor because she's great. So we're going to elect her as a leader to pick the cake flavor. So what flavor would you like? You have to choose either between chocolate cake or cheesecake. Chocolate, chocolate, chocolate. Yes, I was just thinking about the same. Okay, so let's go for chocolate. So Mona said we're going to go for chocolate cake, and now we're all going to go out and buy a chocolate cake and share together. So now that's consensus, and that is Raft. Latency, it's okay. We can just, okay. Caesar latency happens, right? So in Raft, we have two phases. One is leader election, where this phase we elect one server to be the leader, and we need to detect leader crashes and then enter re-election phase if the leader crashes. So this is the phase where we elect Mona as the leader. And then the second phase will be log replication. So once we have the leader, we want to be able to process client requests, and we want to be able to replicate the leader's logs, which ensures consistency and consensus among the servers, which we'll talk about later using examples. Okay, let's first go through leader election. So each server has their own timeout time. After a server timeout, it will become a candidate. And so this is saying that I want to be a leader, please vote for me. So what the server is going to do is going to increment the current term. So the current term represents how many election phases that we've been through and what is the current election number. And now it's going to vote for itself. It wants to become a leader. And after that, it's going to ask the other servers to vote for it. So it's going to send out this request vote RPC to the other servers. And it's going to, three things could happen from here, right? So one is the other servers would just respond vote by basically saying yes or no, I want to vote for you, I don't want to vote for you. And once the current candidate receives a majority of responses from the other servers, going to check, did most servers agree that I can be the leader? If that's a yes, then we're going to start becoming a leader and then send heartbeats to the other servers, act as a leader to handle client requests. Well, the second scenario could be during the process of collecting vote from the other servers, it received a heartbeat from the legit leader. So this is the phase where there is a server that became a leader before the current candidate. So now it received a heartbeat is going to say, okay, now I know there's a leader, I'm going to step down as a follower. So it's going to want to redirect request to the legit leader. Well, the third scenario is the timeout scenario. It's called split vote scenario, where we have multiple candidates, none of them got a majority of responses or a majority of votes from all of the servers. So in this case, it will just time out back and re-enter the election. We can talk more about this later. So how do we ensure leader election works? Basically, there will always be a leader because each server, they can only vote once per term. So whichever server wins the majority amount of vote wins the election. So for example, in this scenario, we have 5 servers. The majority will be 5 divided by 2 plus 1. So if a server receives 3 yes from the other servers, then it can just step up and become a leader. So in this case, if server 0 votes for itself, also received a vote from 2 and 3, server 1 votes for itself, received votes from 4, and now the leader will be server 0. So there eventually in Raft will always be a leader because each server is assigned a random election timeout time. And this random election time would be among, usually, it's not required, but usually among 100 milliseconds to 300 milliseconds, which usually one server will time out first and it will be able to gather the majority amount of votes if its log is complete, and then it will become a leader. So this is the split vote scenario that we mentioned. If 2 machines have, let's say, the exact same amount of vote, but neither of them actually got the majority from the other servers, what happens is that they both will wait for a period amount of time and they will realize that nobody has become a leader and they're in a split vote tie. So they will both time out and re-enter the election state. So now we covered election. Let's talk about log replication. So now we have a leader. What we want to do is go ahead and process client requests. So we want to receive requests from the client. Once the client tells us to do something, we're going to first append it to our own log entry. We're going to remember this command, and we will want our followers to also do the same. So we're going to send out this append entry RPC, asking our servers, can you do the same? I did the same. And then the other servers will respond by appending this command to their own log, making sure that their log is the same as the leader's log. And it's going to send out this acknowledgement saying that I've done what you asked me to do. Now, once the leader got a majority of responses from the other servers, that means it's safe to commit this entry. So by commit, we mean it's safe to execute the command, it's safe to return the results to the client. So now the leader will execute the command, return the result to the client, and it will automatically commit this entry to its own log. And now it will want the other servers to do the same, so it will again send out an append entry RPC to the other servers saying, can you please also commit this entry, because I did. And the other servers will respond and commit the entry. So that was if everything works out really well, right? So what happens if we didn't get a majority of responses from the other servers? Let's just say in this scenario, we have a leader want other servers to append an entry in their own log, but only one server responded and appended this entry to the log. So the other server didn't respond. So once the leader figured I don't have the majority of servers responding me, the server will just simply keep trying and trying again until it gets a majority amount of responses before moving on, because at this state, it's not safe to commit this entry yet. We've been talking about log entries for a while. This is what it looks like. You have three things, basically. The current term records which election term we're at, how many elections we've run through, also the command for this entry to execute, and also obviously you have the index of the log. So servers can crash, right? When one server crashes, there could cause log inconsistency issues. For example, server 0 and 2 has a longer log compared to server 1. This just means that server 1 could be partitioned out. It could crash during some point. Now server 0 and 2 has a better and more complete log. So how do we resolve this issue? How do we detect inconsistencies during Raft, during the processes, and how do we fix them? There are basically two parts. Again, there are two phases, right? The leader election and log replication. So during leader election phase, you always trust the leader's log. You do not elect any server to be the leader if the server does not have a complete log. We're going to talk about examples of how to tell whether the candidate has a good log or not. Also, we guarantee that there's no holes in the log, basically meaning we always append commands to the end of the log. We never ever skip any entries. Also, during log replication processes, we repair inconsistency by copying the leader's log, which we'll also talk more later. So let's start by talking about how to fix inconsistencies or how to elect a candidate that has a complete log. Remember that we send out this request to vote remote procedure call during the candidate election process. Basically, one server sending this message to the other servers asking, hey, can you vote for me? I'd like to be a leader. The request vote RPC contains the following information. It has the term, which again is the candidate's current election term, how many elections it has been through, and what's the current term. And 2, the candidate ID, so the server's ID has to be unique. 3, the index of the last log entry and the term of the last log entry. This is how we use it. So we can imagine ourselves as a server. We're the current state machine, the green one. As the green server, we have a blue server candidate that want us to vote for it. So we got this message from this server, and we have all the information about our state machine and the other candidate's message, right? So what we're going to do, we're going to compare those information. We're first going to look at what's the term. So in this case, the candidate has a lower term number than ours. And our IDs are different, which is expected because it has to be unique. And now we have the same last log index and last log term. Raise your hand if you think we should vote for this candidate. Raise your hand. Great. Raise your hand if you think we shouldn't vote for this candidate. OK. And I'm just curious, can you please explain? It's OK if you don't, but if you want to, why do you think we should vote for the candidate?
Because the green one is already moving on to the new term, so the candidate is still in the old term, so that's why.
So we should vote or shouldn't vote? We shouldn't vote. Oh, OK. Yeah, correct. We shouldn't vote for this candidate because we have a higher term number. That means it's more likely that our log is more complete because we've been through more election terms. We do not want to trust the candidate's log at this point, so we reject its vote. Reject its request and do not vote for it. So another example, oh, quizzes, OK. Another example, so again, we are the blue machine. We're the green machine, and we got a message from this blue machine asking us to vote for it. In this case, we have the same term number. We have a different log index. Ours is 4, the other one's is 3. We have the same term. Raise your hand if you think we should vote. Oh, raise your hand if you think we shouldn't vote. Oh, wow, cool. Looks like you're all paying attention. I'm happy. Okay, so we shouldn't vote because our last log index is longer. That means we have a longer log. We do not want to trust the candidate, so we do not vote for the candidate. We shouldn't vote for some server that does not have the best log. And now this example. So now we have the same term, different IDs. We have a higher index and the same term. So raise your hand if you think we should vote. Raise your hand if you think we shouldn't vote. Oh, okay, everyone got it right. Yay, you're right. So we should vote because now our last log index is longer. That means our log is longer. Sorry, what am I saying? The candidate's log is longer, so we do want to trust the candidate this time. We do want to vote for the candidate to become a leader. And now, we went through how do we make sure we elect a server to be the leader that has the most complete log. Now let's talk about log replication. How do we detect and then repair inconsistencies in log replication process? So remember that we say when there's a leader, we want to send out this append entry RPC to the other servers, wanting them to append our current log, which is the leader log, to the other server's log, making sure that they are all the same. So this append entry RPC has the following information. It has the current entry, everything about the current entry. So it has the index, the term, and the command. And then it also has a little bit of information about the preceding entry. Basically it has the index and the term. So now how do I use this information? When we want, as a leader, now imagine ourselves as the leader machine. We want our candidates to append entry, right? So we're going to send this entry 5. So we want to append, we want to ask the candidate, to the other servers to append entry 5. So we're going to send everything about entry 5 and a little bit information about entry 4. We're going to send all of the information in the append entry RPC to the other server. So server 1 will receive this message. And what it will do is it will compare at index 4, do I have the same term as the leader? So now in this case, at index 4, we have term 2, so does the leader. So now it's safe. We can basically assume two things. One, we have the same command as the leader's log does in this current entry. And two, all the preceding entries are exactly the same. So now it means it's safe to replicate the leader's log. So now we're going to simply append entry 5 to our own log. Now what about it? What if it doesn't match? So let's say the server 1 at index 4, it has term 1 instead of term 2, which is different from the log. And now we cannot assume that our logs are the same. So we'll simply reject leader's request. And we're going to tell the leader, I'm sorry, it does not match. I'm not going to append your log. And the leader simply won't give up because we're the leader. We know that we're right, right? So we're going to try again by sending more information. So now it's going to send entry 4 and 5 and a little information about entry 3. So it's going to send all of those information to server 1. And server 1 will say, OK, now at index 3, do I have the same term as the leader? And now, as you can see, they have the same term at the same index. That means, again, we can assume those two things. We can assume everything in the current entry is the same, and everything in the preceding entries are all the same. So now we're going to just simply append the entries log by appending 4 and 5, because we always trust the leader. So now you've fixed the inconsistencies in the server's log. So this log matching property in Raft basically says if for each log entry you compare the index and the term, if at the same index you have the same term, you can assume, again, two things. One, you can assume that these two entries store the exact same command. And two, all the preceding entries are exactly the same or identical so that you can safely append the entry to our own log. OK. We have consensus algorithms that help us with lots of problems, to fix lots of problems. But there are also problems with consensus algorithms. And I drew this panda, so I'm really proud of it. So what are the problems with consensus algorithms? Well, first of all, we say that the messages communicate with the servers communicate with each other by sending messages. And that means we're going to have overload, right? Overhead. We're going to have to deal with duplicate messages, out of order messages. What about messages that are lost? I've never received the message. How do we know, how do we handle latencies in the machine or in the network? The servers could locate very far away from each other. So how do we deal with those kind of problems? Well, again, failures. We could have the leader failure. We could have followers that fail. How do we handle partitions? How do we make sure that our system can still work with and without those failures? Confidentiality. Who has the right to read your data from the server, and who has the right to write to your server? And I really apologize for this really creepy human head. I do not know how to draw it in a less creepy way. So if you have any ideas, talk to me afterwards. And dinosaur, that's much better, right? It's not as creepy. So we could also have malicious peers where, how do we handle malicious and misbehaving peers? We do not want them to abuse the information in the server. One example of having malicious peers is this Byzantine generals problem. So this is basically you have two generals that try to agree on one thing to do. They both have to agree on whether to attack a castle or retreat from it. So if they both agree on one thing, then they win, right? If they both agree to attack or retreat, they win. But if if one chooses attack, the other chooses retreat, then they just lose. This problem seems really simple, but the problem is that they can't communicate face to face. They have a messenger that will communicate for them, send messages to each other. So the problem becomes complicated when you do not know whether the other server is a traitor or not. And how this applies to distributed system is you can have a server that acts perfectly fine. You can't really tell what's going on with the server, or it's acting as a normal server, but instead is a compromised server. It could send malicious things to other server to compromise them. In this case, it's really horrible because it could abuse your information to use it to do something else. There are algorithms that are modified to be Byzantine fault tolerant. There are modified Byzantine Paxos and Raft. But the problem with those algorithms is that their overhead is even higher. It's more expensive when you want to be fault tolerant to Byzantine failures. Some of the takeaways to this talk. Phew, finally getting to the end. I'm glad nobody has fallen asleep yet, so that's good. Yay. So in the industry, when you want to implement consensus algorithms, well, the first thing is try not to do that, because understanding the algorithms and being able to implement the algorithm are two complete different things. When you're implementing the algorithms, not only you need to follow it step by step, you'll have to prove why your algorithm works and how and why it works correctly, right? So if you can find an algorithm that has been proven to work correctly, then it's better to use that service. But if you do have to implement your own algorithms, you need to think about, is my system resilient against the issues that we've discussed? And more importantly, do I want it to be resilient against those issues? It's always a trade-off between reliability and complexity. So it's up to you, the developer, to determine whether your system, your algorithm needs to be resilient against those issues. In the academia, when you're designing consensus algorithms, you need to think about, on top of consistency and correctness, you want to be able to design an algorithm that's understandable to other people. You want people to be able to understand your algorithm so that they can use your algorithm, adapt to their own system. And that concludes my talk. Thank you. I'm Yifan. I'm from Northeastern University. But wait, before you do the clapping thing again, can I just ask how many of you would go for cheesecake? Raise your hand. Oh, wow, cool. What about chocolate cake? It's 50-50, so I can't pick. OK, well, thank you. Now I can take questions, and thank you for listening and for not falling asleep. questions. I love the awkward silence after the talk because, like, it's great. It's just I don't get embarrassed if I can't answer a question. So I don't mind if you don't ask questions, but if you want to, I'm happy to. Yeah, go ahead.
Cheesecake Factory has this Untitled Chapter cheesecake.
Oh, it's like a combination. Okay, that's like the most important takeaways for me for this conference. Thank you for letting me know. What's it called? What's the name? What? Oh, we'll talk later after. Anybody has any questions? Okay. Well, you can always find me afterwards. I'll be around. Thank you. I will post my slides on Twitter.